So when we talk about any software or any technology, I think the first thing that we need to do is to look at the software under the hood, or that means how does it work. And often in the old days, when you open the hood of a car, you could see the engine, you could see all the components, and you could see how they work. But if you look at any of the modern cars these days and you open the hood, you find another hood or a black box underneath. So, which means that most of the software and most of the things these days are hidden from the people. Earlier, and because of the technology, it wasn't so advanced, so everything was exposed, was visible. People could see and interact with the things at a very low level. But now, most of the time, we are just dealing with a high-level interface, and we don't know what's going on behind that. But today, we want to go, and take a look at CSI Call and see where it came from. So under the hood of CSI Call is actually this book, which is called Structural Cross-Sections, Analysis and Design, written by myself and one of my students at that time, Dr. Fawad, who is now in Canada as a faculty member. So we wrote this book at the same time that we were working on some of the development of CSI Call. So both the programs and the book are actually interconnected. So you can find most of the theoretical background for CSI Call and other programs in this book. Now, I want to emphasize just briefly to see where these things are coming from. So we can look at CSI Call, the output that we get, response that we get is three kinds. One is the section response related to section itself. One is related to this capacity, and one is related to its moment curvature. And you get a lot of further response from there. So I want to just share with you how these three main categories of response are computed. So first of all, the section properties, area of cross section and all, is based on general rules of integration. I think many of you know already. So we can use these rules to integrate the area, moment of inertia, shear areas, and all of that. So that's one thing. Second one is that once you have a composite section, then we also bring in the modular ratio, because different materials have different elastic modulus. So you calculate the modular ratio and you modify that to calculate the elastic stresses. So this is the modification to the basic equation for composite section, which is also well known. This is where things get interesting, which is, I think, quite unique to the program that we're talking about. When we talk about a general cross section, we actually define the cross section to be of a very general form, a cross section which is made of general zones, each zone having its own material or properties, and each material is simply defined by a stress strain curve. So we basically, when we develop the theory, we don't think about concrete or steel or anything. This cross section could be made from bamboo, from plastic, from anything. As long as we have the stress strain curve, we have the configuration, we should be able to solve this cross section. And based on that, then we develop the general representation of the equilibrium equation. I'm just going very quickly to remind you how these things work. So we have a cross section, which is now a reinforced concrete section, a composite section, and also we put in some reinforcement, rebars, and also post-tensioning, because post-tensioning, once again, is just a material. And then based on that, if it is undergoing a certain deformation, we can write the general equilibrium equations in that way about, axial load and to any arbitrary axis. So after having those equations, which are basically integration of stresses over the area for which they are assigned, we get the total stress resultants. And then we can use this, analogy that if you have a beam cross section, and if you look at the typical way that we define the stress strain curve on it, then we can assign the concrete curve, and we can read the concrete stress at the specified strain of 0.003. We can read the steel stress at specified strain, and then we can just add them together. And because there's no axial load, so we just get moment equilibrium, and we can calculate the moment capacity. So that's the simple application of that concept to a very simple cross section. Now, same thing can be applied to three quantities, moments, and as well as the axial load. And you get now not one, but you get three numbers, and you get this interaction between axial and flexural capacities, which is called the axial flexural surface, interaction surface. This interaction surface we can subdivide, or we can visualize it in two ways. One is we cut it vertically We look at PM interactions, moment versus axial load interaction, or we cut it horizontally. We look at the two moment interaction, MX and MY interaction. So we get full behavior understanding of the cross-section capacity for a given strain constraint, which is 0.003, 0.035. So this is a arbitrary surface, failure surface we generated for particular strain and stress condition. And actually, when I teach this one, I normally give the analogy of a watermelon, where you have a watermelon and you cut it vertically and horizontally, and you get those information. So students tend to remember this more clearly, how this came through. Now we will show you how this interaction surface is actually generated, and this is part of CSI Call program. You can actually see it by yourself. You can just play this animation. It shows you for each cross section how the neutral axis is being rotated and the neutral axis is being changed, and the corresponding points on the interaction surface being generated until the entire surface is complete, and then we can use it for capacity calculations. So this animation is useful to understand how it works, and also is fun to watch. So that interaction surface that I showed you is theoretical. It did not include the codal provision. So we have to now bring in the codes. So in CSI Call, we can handle that many codes, I think 14, 15 codes on the app. And these codes come in to specify material models, stress strain curve, capacity factors, material factors, and slenderness and all. So we first determine the general capacity, and then we enforce the code-based constraints on top of that to get what is the code specified. So when we bring in the codes, the blue line is the theoretical curve that we computed, and the orange line is the ACI code curve version after applying all those factors that I mentioned. So that means you can see that we reduce it by certain numbers to include factor of safety and other constraints for each code. So that's the figure from ACI 31821, and that's how they interpret the interaction curve, theoretical and the applied or applicable based on, and remember, this is still based on ultimate load. The actual loads are somewhere in between. So this is still a way far from the theoretical capacity. So that's about the capacity. Moving on to the curvature. When we have a curvature in a section, obviously, then we get the stress strain curves like that. And then in this case, we equate them for a simple beam based on the code, and we can derive a simple formula, which is a simplified form of the general formula that we have used. So code equations are just very specific cases of very general case applied to rectangular section with rectangular stress block and so on. Now, if we move forward to a general curvature case, which is not with the code, and we go from 0 to maximum possible deformation, if we apply load to a beam, and then beam deforms, and then we get a curvature, and then for each curvature, so then if you see that, then we have once again the steel and the concrete stress strain curve that we have used in the cross section, but this time we are not limited by the 0.003 strain value that we used for the capacity. We allow it to be free and depend on the actual curvature. So when that is the case, it can come from any location. So any strain corresponding to a curvature can go back, read the stress, and get the equilibrium equation. And then based on that, we can then determine the moment for that curvature. So this way we can generate the moment curvature point for a given curvature, assumed curvature. And so to conclude, we have this one, and if you fix the strain and vary only the neutral axis depth, you get capacity curve. And if you vary strain, vary KD, and maintain load equilibrium, you get moment curvature using the same equation. So both of them are actually using the same equations, just using differently. But moment curvature gives us far more information than capacity ever can, which I discussed in another video. One more thing, the last item that I want to discuss very briefly is that this is an interaction that is not normally discussed. And this is an interaction between axial load and the curvature and the direction of curvature. And if you plot those in a surface, it will look something like that. So this is very important for columns when they are axially loaded, and we are interested to find curvature relationship in with different directions. So now if I compare them side by side, the left-hand side is a moment, is a curvature versus axial load plot on different section of the cross section. Right hand side is a load and moment plot from the capacity. So two are very different, but they look similar in terms of how they behave. One is derived from moment curvature, another one is derived from capacity curve. So if you move that, and you can see, if you cut that, you get the TM interaction. And if you cut this one vertically, you get an axial load versus curvature interaction. So you can see how the curvature capacity decreases as axial load increases. And then on the right hand side, you see the moment and moment plot interaction between them. And similarly, on the left hand side, you'll see the change in the curvature capacity along the different sides of the cross section. So that's how we can interpret the whole cross section capacity and curvature based on the equation that I saw. And all of this that I've shown you is implemented in CSI Call, and all of the diagrams are taken from there.